All right, so welcome to this webinar, and we're treating the topic just like publicly have always mentioned, introduction to networking for security professionals. So in this webinar, we are going to be touching a lot of foundational concepts for networking, right? We're going to touch all that has to do with networking devices, what a computer network is, network types, network components, the internet protocol, um, routing, how communication is done on a network. We get to understand this basic foundation of networking. So, and right here, we have our expert with us, a networking engineer, the person of Mondelo Barakuma. So he has been into this field for a while now, and he's going to be walking us through this. He is CCNA certified, that's certified, Cisco Certified Network Associate. All right, so which means he has a very, very wide knowledge about networking. You can check him out on LinkedIn, and you'd see that majority of his post has been on network simulation and a lot of stuff that has to do with networking. All right. So, and after this webinar, we're still going to have another with him, which is going to be on the Cisco Packet Tracer, where he's going to give us a deep dive into how we can use and understand the Cisco Packet Tracer, because in the cybersecurity essentials course, which is the reason why we are doing all these preliminary courses, we are going to be making use of the Cisco Packet Tracer, and we want the situation whereby everybody knows or everybody is already conversant with the software, and we'll be able to do some stuff. A lot of concepts will no longer be new to us when we are asked to do some live when we're asked to do some live actions, all right, on the Cisco Packet Tracer, because it's going to be a live workshop and it could be a do as I do, all right. So we need everybody to be very, very conversant with the platform. So that's why we are going to be having that workshop. So Mondelo Barikuma is a CCNA certified network engineer with hands-on experience as a CCNA instructor and expertise in advanced networking concepts. He's proficient in Python programming, Docker, Linux, and automation tools like Git and Ansible. He's also skilled in network automation and VPN implementation, with a passion for leveraging cutting-edge technologies to optimize network infrastructure and security. He's adept to troubleshooting, designing, and deploying scalable network solutions, and is committed to continuous learning and contributing to innovative IT solutions that enhance efficiency and reliability. All right. With lots of joy, let's welcome instructor Barikuma Mondelo to the stage. You're welcome, Barry.
Thanks very much, Badi. Good evening, everybody. Please confirm if you can hear me, please.
Yeah, we can hear you.
Okay, cool. All right. Good evening, everybody. I'm really glad to be here. Honestly speaking, it's like I would say it's a thing of joy actually to share knowledge with people. And though the turn-up wasn't as expected, but I mean, it's one of those things. This is not like the first. Like I say, this is not the first time I've experienced something like this. But yeah, it's all good. It's all good. So we'll have to start. Yeah, we just have to start ASAP. So as stated earlier, what we'll be talking about today would be like an introduction to networking, right? I know many people here are going in for a cybersecurity role and all that. But the truth is, you have to really understand networks because that is where the foundation of security starts. That's where your security starts from, securing the network and all that. So I will give like a, it's just going to be like a summary because I believe you guys will be enrolled on the course later on. You guys will be enrolled on the course. So I'm going to give more of like a summary of what networking is, an introduction to the field of networking generally. So I would share my screen. So maybe we'll just talk about, I've been busy, so I just had to come up with something as simple as this. Can we see this? I'm currently sharing my screen. Is this visible, please? That's a reaction or something.
Yeah,
Right.
yeah, sure.
Right. So, like I said, introduction to networking. And the first slide here is asking what is a network, right? So a network in basic terms, a network basically is connecting two or more devices together with the aim of sharing data between both devices, right? You know, for example, we want to share things via Bluetooth. You know, share. I think then they were sharing songs via Bluetooth, right? That's a network, right? The fact that there must be a connection before data can be shared. That's what a network generally is. So your networking devices, you're connecting them together because you want to share. That's the sole purpose, to share data between them. Now, this modern age, prior to this modern age, networking generally, like between devices, has always been kind of like custom. And I'll explain now. But let's move on to um, network media. So we should know this by now that there are two types of connectivity to networks. The media, which data goes through, which is either wired or wireless. You know, wireless either using the Wi-Fi, right? Then wired is either using, maybe you're using a coaxial, or you're using an Ethernet or a fiber optic. You know, every in as much as you connect wirelessly to an access point or to a Wi-Fi, it's still, the underlay itself is still a wired network, right? When you make phone calls, you're starting with frequencies, microwaves, and all that, but it still goes down to the wire. So the backbone of the network generally in the world is wired. And one one of the pros of wired network is that it's actually faster than your wireless. You know, it's not affected by will I say the weather. It's not affected by the weather, or any or obstructions or obstacles and all that. The wire has always been, for me. I actually prefer wire network though. Has always been there, and it will forever be there. And the second is the wireless, which I mentioned, which is the Wi-Fi connection or satellites, just like when I say your TV, for example, you're working with satellite. You know, you're working with satellites, and it still goes down to the coaxial, down to the decoder. That's sort of the same. So those are like the basic, those are like the major medium where data rather flows through. And in networking, sorry if I'm too fast, please. You can always ask questions. I'll definitely respond. But the intro part is actually very straightforward. When we keep going further, that's where we actually have to take our time. So there are actually topologies, we call them network topologies, right? And there are more than the two that are here. There is the LAN, which we can see here. So if we look here, this LAN, right? This is a LAN. This is a LAN. So basically, a LAN is just like a building. Imagine you have a building, 2 stories or 3 stories, and they all have computers. Each of the floors, there are computers there, and they are all connected together. That's a LAN, right? That's one local network. those devices are located in one building. That's a LAN. But in situations where you have to like try to say you have a branch office, for example, right? Let's say you have a headquarters somewhere in Port Harcourt, and you have a branch office in Lagos, another branch office in um, what's it called? In, let's say, Abuja, for example. Now, what you have to do is, if you want to interconnect those, you want to connect those offices together, that topology now is your one topology, wide area network, because you're going beyond the building, the original building which you started with, right? That's your one. There is another one, PAN, personal area network. This is like connections via your Bluetooth, for example. You know, Bluetooth has a range of, they say 100 meters, but I've never seen any Bluetooth that goes up to 100 meters. Maybe there is, right? But yeah, it has like a range of 100 meters. And those kind of devices, your Bluetooth, your RFIDs, or rather, yeah, RFIDs, they have to have like close proximity, right? So that's a network now is known as your personal access network, right? Your Bluetooth, your RFIDs, you know, then the next one is your MAN. MAN is still using the branch offices and the HQ. Now, let's say we have a HQ in Port Harcourt, and we still have a branch office still in Port Harcourt. In as much as they are not geographically, they're not in the same location, right? Geographically, but the distance, you cannot compare the distance between a branch and a HQ in Port Harcourt with a branch and a HQ in Abuja. The distance is way, way different. So demand basically is just connecting connecting offices that are within the same geographical region. Okay, so let's say, for example, let's say this central now is in Port Harcourt, and this branch is also in Port Harcourt. They have no need of going through through like a, let's assume this ISP, one is in Port Harcourt, one is in Abuja. They have no need going directly, to that ISP like that. They can just have like they call it a direct connection, or like a lease line, basically within the same city. Okay, that's your MAN. So these are the various network topologies that are available: your LAN, your WAN, your PAN, and your MAN. So the LAN is the local area network. WAN is your wide area network. Your PAN is personal area, and your MAN is metropolitan area network. Okay. So now, prior to the current age where we find ourselves, right? If devices were to be networked, if devices were to be connected together, for example, you start a company and you want your devices to be networked together, what you have to do is all the devices must be of the same vendor. So if you're getting a HP laptop or a HP printer, every other device must be HP. Or you're getting a Dell or you're getting an Apple, every device must be the same. This was because back then, like in the 70s, in the 80s, and so vendors were made to have their own custom, they call them models, right? Custom models for their devices, right? So it means back then, if you had a HP computer, a HP computer would not be able to communicate with an Apple computer because Apple had their own model. Then HP will have their own model. IBM also had their own model. So every vendor had their own model. So an office will have to have all devices of the same vendor in order to have a successful, in order to have successful communication between those devices. But a time came where some group of individuals, a body, decided to say, okay, what if all devices could make use of just one model instead of having each vendor make their own model? What if all devices could have just one model so that every device, no matter your vendor, can communicate? That's what this reference model, that's where it came about. Okay, so the first one that came out was the OSI model. OSI itself stands for Open Systems Interconnect, and the reference model, these are layers in the reference model, right? And these layers are let's say they are the layers that, or any data you're sending, even as I'm talking right now, right? They have to go through these layers before they can get to the destination. Okay. So every device now, that's the reason why you can send something via Bluetooth from different devices. You can send via Zenda or any other means, because each device is making use of this reference model. But currently, the reference model we are making use of now is the TCP IP model, right? The TCP IP model. Though the layers on the OSI and the TCP, they all have the same function. But if you look at the TCP, it doesn't have 7 like the OSI. It just has 4. So there were some layers that were merged together to form one on the TCP IP. So every device currently in this world is making use of TCP IP model. Now this model now is it kind of like helps, not kind of, it actually helps devices to communicate, because the data you're sending has to go through each of these layers before it can get to the destination. Okay, and in each of these layers, they have protocols that are running in each of them. For example, the application layer, what it does is it provides the protocol required for the application you're using. For example, your web browser is an application. If you want to go to a website, it has to use a protocol, which is the HTTP. So that's the work of the application layer. It provides your software. It provides it with the application protocol required, right? Provides with the required protocol required for that data. Then the transport layer itself, what it does is it's okay. It works with port numbers, and what that means is it's what makes your delivery reliable when you're working with TCP, for example. It gives that reliable delivery from one point to the other. That's why when you access a web page, you can get everything on that web page. It's because of this transport layer. Okay, you go to a web page, it makes use of TCP. The transport layer is making sure that every image, every text, every color is delivered to you successfully, right? Then the internet layer, this is where we talk about IP addresses. Right? That's just basically what is here, IP addresses. Okay, we'll talk about addresses very soon, but that's just what's here. Then on the network access layer, um, on this network access layer, it contains, if you look at the OSI, it contains data link and physical. So now I want to talk about the data link itself. The data link now it contains MAC addresses, and these are layer 2. So network layer is also known as layer 3. If you look at the layers of the OSI, for example, we have layer 1, layer 2, 3, 4, 5, 6, 7. Your data link is layer 2. So if someone is talking and the person tells you, okay, the layer 2 address or layer 2, that you know that, okay, the person is referring to the data link. So in as much as we are making use of the TCP IP, right? When you hear someone say layer 2 or layer 7, they're actually referring to the layers of the OSI, but they all have the same functions. So the network here on the OSI is the same as the internet here on the TCP IP. The transport is the same thing. Then application, presentation, and session. What happens in the TCP IP is they merge all of them together and just name them application. Then here on the data link and physical, the physical is is the wire itself, that's the cable or the medium where your data goes through. So the wired, the wire itself, the cable itself, that's what the physical is all about. And the data link is your addresses. And these are the technologies that operates on this layer. Okay. Any questions so far? Any need for clarification before I move to the next? If you're good, you could just do a thumbs up, and I could just move on to the next. Right, cool. Okay, so yeah, for like I said, we are still working with the distributed TCP/IP. Okay. And if you remember when I said something, I said that if you're going to a website, your what you're doing before it leaves your laptop, it goes through these layers before it leaves your laptop. The process of say I go to www.google.com. When I've entered that website, it enters from the web from the browser, right? It goes to the first layer, the application layer. Now, in the process of your data going down the layer, that process is known as encapsulation. Encapsulation. That's because every time that data goes to a new layer, it has, like, I'll call it like, it has, I'll just call it something for now, but I'll explain it when we go further, okay? But it has something added to it. By that, let's look at this, for example. This guy wants to send an email, right? He wants to send an email, and he sends it. This is data. He sends it to this is the application layer. It sends to the application layer. It's data. When that data now has gone from the application to the transport layer, right? It has a header. This is something I talked about. It has a header added to it. Now, this is the encapsulation, right? I'm talking about rather. This is the encapsulation I'm talking about. So for every time that your data goes through those layers, it is encapsulated with something new. So remember, it went through the transport layer, it had a transport header encapsulating the data. When it went to the internet layer, the network header was encapsulating. You can see this is the original one that's here. The transport encapsulates. When it went down, the network encapsulated. When it went down, the frame, this is your the layer 2 now, data link encapsulates. So every movement from a layer downwards, right? If you look here, it's passing down the deck. Let me zoom in a little, sorry. So passing down the stack, actually. Whenever it goes down, it's encapsulated with a new header, always encapsulated. So this is what data encapsulation is all about. So no matter what you are doing, as you can hear my voice now, the voice, they are moving in packets, they are also being encapsulated. That's generally what the world operates with. You text someone on WhatsApp, it's been encapsulated. It has to go through these layers, it's been encapsulated to make sure that it's successfully delivered, right? So I mean, for devices, I don't think a device without any of these reference model, that device will not work successfully. It won't work successfully, right? So your encapsulation, like I said, whenever it's just having your data, having headers appended to your data, rather prepended, it's coming from the back here, to your data, right? As it goes down the stack, having headers which they are prepended to your data as it goes down the stack. That's just what encapsulation is all about. And I said that um, everything you do on the internet, everything, like I said, everything you do on the internet is encapsulated. It's either going to use TCP here on the transport or UDP, whether you're using HTTP or you're using POP or anything at all, right? It goes down the stack, it must be encapsulated before it's then sent. This is your layer 1 right now, before it's then sent as bits on the wire, right? So all this encapsulation, when it gets here at layer 1, it's then converted to bits. Any questions so far concerning this encapsulation? Please, you guys should ask, in as much as you've been enrolled in a course or so, at least understand its basic explanations. Any question, or should I go to the next? Should I move on to, okay, cool. Okay, so now I'm going to talk about the data link layer, and from our OSI, that is layer 2. Here, talking about this now. The data link layer is where, okay, before I talk about that, let's talk about something. Let's talk about addresses, right? That is for devices to function in the network, for devices to be able to communicate in the network, it must have two types of addresses. These are your layer 2 address, that's the MAC address, and the layer 3 address, that's your IP address. So a device without either one of them will not successfully communicate in the network. Right? It depends on what you actually want to do, because I mean, working with Bluetooth devices, for example, they don't use IP addresses, but you have to know that for your device to successfully communicate, it must have a MAC address and an IP address. Every device that connects to the internet or that connects via Bluetooth or via Wi-Fi, every device that does that, they all have MAC addresses. If they didn't have MAC addresses, they can't communicate. Right. So, and now at the data link layer it makes use of MAC addresses. MAC addresses, they are, I wish I didn't write it down. Okay, MAC addresses, they are 48 bits, right? Or you can call them that you can say they are 6 bytes, right? 6-byte hexadecimal, which if you convert them to binary, they are 48 bits. So they are 6 bytes hexadecimal values. So an example of a MAC address will be something like this. Say, this is an example of a MAC address, right? They are hexadecimal values and they are 6 bytes. I hope we all know this, but 4 bits, or rather, 8 bits make 1 byte. Okay? 8 bits make 1 byte, and each of these hexadecimal numbers are each of these numbers are 4 bits. So 2 will be 8 bits. So this is 1 byte, 2 bytes, 3, 4, 5, and 6. 6 here. So this is an example of a hexadecimal of a MAC address. So MAC addresses are hexadecimal, and okay, let me just say that hexadecimals they count from 0 to 9, then A to F. So you can get from 0 to 9, A to F. These are correct. Any hexadecimal or any letter or number within this range is a correct hexadecimal value. So that's what your MAC address is like. So you could have something like this, or you could have another device with a MAC address of 0, 1, 2, A, B, C, 3, 4, and then let's say 9, 8, B, F. This is also an example of a MAC address. So a device must have a MAC address for it to, be able to communicate on a network, right? Because when you are sending data to different devices, that address must be included. That's why I said the device. So imagine if you want to send a message to, for example, I want to send a message to Rollins and I don't know his MAC address. I don't know his name. That means I can't send a message, right? So that's why I said a device must have a MAC address, and also a device must have an IP address. We'll also talk about IP address when we go on further. But one thing we should know is that both of them are different. For example, now I said here that the MAC address is 8-bit hex, for 6 bytes hexadecimal. The IP address itself, IP address is IPv4 right now. IPv4 address is 32 bits. They call them 32-bit DDN. DDN stands for dotted decimal notation. By DDN, it just means this, say for example, 192.168.1.1. All these numbers together, all of them, if you count them in binary, they are 32 bits. Each of these numbers are 8 bits each, 8 bits each. That's 1 byte each. So, yeah. So this is an example of an IP address, right? And this is an example of a MAC address. So devices must have MAC address and IP address. But now the difference between a MAC MAC stands for Media Access Control. So the difference between a MAC address and an IP address is this. The MAC address itself is permanent. Permanent meaning a device with a MAC address. For example, this is our MAC address. If a device has been assigned this MAC address, this will forever remain its MAC address. Then if, say, the device moves to another city or another network, this is still its MAC address. So you can look at that like your name, for example. If you move from wherever you are now to another city, it's still your name. It's forever going to be your name till you die. You know, in as much as legally you can change your name, but at least you get my point. As long as you've been assigned, okay, this is your name is John, or your name is Luke, or whatever your name is, that will forever be your name. That's just what a MAC address is. Telling the computer that this will forever be your MAC address until you cease to exist. But now the IP address is now different. IP addresses can change. Okay, IP addresses can change. That's the difference that's one of the differences between both of them. So, for example, let's use a classroom, for example. Now, you go to a classroom. Let's say the name of the class is, let's call it Science for A. Right? Let's say there's a classroom named Science for A. This is the classroom now, and each of these, and in this classroom, the classroom has like seats with numbered 1 to 100. So you could decide to, on the first day of class, you could sit on seat number 5, right? On the second day, you can sit on seat number 8. On the third day, you can sit on seat number 99. That's just what the IP address is like. So, for example, I connect to a network with my laptop. I can be assigned this IP address, right? If I disconnect from the network and I connect later, let's say after some days, I can be assigned number 17. I won't be assigned 1 again. If I leave the network and I connect again, let's say I turn off the Wi-Fi and I turn back the Wi-Fi on, I can be assigned an IP address of this. That's what I mean by difference. That's why I said the MAC address is forever the same. So this MAC address will not change. Even if I leave the network 200 times, it's still going to remain like this. But if I leave the network 200 times, there is a possibility that I will not be assigned this IP address those 200 times. So that's why, say, look at it like a classroom, for example. You could sit down on seat A, sit down on seat F the next day, or seat 100 and all that, because that is not permanent. But your name, in as much as you sit down on any seat, your name is going to remain your name, right? And devices must have this to communicate. Without this, the device cannot communicate. Okay. Any questions, please? Any questions, please? You all should ask. If you're good, you just throw a thumbs up and move on. But please ask questions if you want to. Should I continue? Only Rollins is responding. Are you guys okay? Okay, I'm seeing another person. Cool, cool. So this is now. Remember we said something about encapsulation earlier, right? When the data moves down the stack and all that. This is how your data is represented in layer 2. That's the data link layer. When the whole encapsulation and all that has been done, this is how it's represented. From here, remember source MAC address, destination MAC address. These are layer 2, layer 2 lingo right here. And this is the data you want to send. Here, this is where your, coming down the stack, this is where your layer 3 is packet, right? That is where it is here in the type length, right? And this is for error detection. So let's just look at this now. This is preamble and start frame delimiter. What it does is just basically, it tells the device to like be in sync, like the receiving device should synchronize itself with the sender. Then this is the destination MAC address. That is, let's use the names, for example. I want to communicate with Rollins. We are both in the same classroom and I want to communicate with him. What is his MAC address? His name is going to be here. So the destination MAC address will be the device you're trying to reach. Then the source MAC address now will be me. I'm trying to reach Rollins, a source MAC. Then the type here, we'll talk about that, but what will be here now is be the IP the IP version that's what's going to be here. IP, so like the type will be IP. Then here will be the data, which is what you're trying to send, and this is for error detection. So if you're accessing a web page, for example, this is how at layer 2, this is how you would see your data at layer 2. I have only saw Wireshark because I would have shown you guys what I meant, right? So this is the representation of data in layer 2, and you'll start. Okay, these are like the sizes of each of them. Remember, I said your MAC address is 6 bytes or 48 bits. So this is 6 bytes, 6 bytes, 2 bytes. This is from 445 to 1500. Should be more than that. Else is considered a giant. And this is your start from the limiter. So this is how your data is represented at your data link layer. And I said also, data link works with MAC addresses. Please, let's not forget it. Now, the network layer itself is the IP address I talked about. And now, an IP address itself is divided into two parts, the network portion and the host portion. And I'll explain. This part, for example, okay, before I talk about the network portion and host portion, we have a subnet mask. And the subnet mask, what it does is it gives us tells us where our network portion is on the address and where our host is at. All right. So if you look at the subnet mask now, 1, 2, 3, 4, there are 4 numbers in between the decimals, and same the IP address. If you map each of these numbers to the 255, right, that tells you the network portion. You can see that there are 3 255s. It means the first 3 numbers will be the network. But we'll talk more about that. Let's just keep going. So the IP address is divided into 2 parts, the network portion and the host portion. It means that for every device, for a device to say that they're in the same network, it means the network portion will be different. Now, let me go back to our analogy of classrooms, the science hall A we talked about now. I said in science hall A, there are 100 seats, numbered from 1 to 100. Now, we can say science hall A is a network, right? I could decide to sit on seat number 5. That is my host portion of my IP address. I could decide to sit on seat number 5. So if you go to science hall A, seat number 5, that's me. So just using our brief analogy, right? Using our analogy, let me type what I mean. So science hall A, seat 5, right? This is now what's an IP address. So this is going to be the host portion, because anybody that is in science hall A can have up to 100. We can have up to 100 people in science hall A, right? We are all in the same classroom, so we can see that as a network. So devices that have the same network portion, devices that have the same network portion, the IP address, they are in the same network. I don't know if you understand, or should I go back, please? This part is very tricky. If I should go back, please just let me know. Let me start again from the top. Kuven, right? I can hear you. I can, yeah. Say what you ask the question. Can you unmute yourself? Rollins, someone to ask a question. I don't know if you can unmute yourself. If you can't unmute yourself, you can just. Okay. I hear you. Is someone talking? I'm down.
The definition. Hello.
Yeah, I can hear you now.
Okay. Okay, so I'm not getting the full definition and the explanation for this division of IP address. I don't know if you could just at least just give us some little explanation. And the subnet max, these 225 and these kind of like I've learned it before, but it's kind of like still giving me some I need some extra explanation. So please, can you help us out, sir?
Okay.
Yes.
This subnet in itself is like another.
Hello?
Yo, can you hear me?
Yeah, I
Yes,
can
I
hear
can hear.
you.
Okay. So as I was saying, subnet in itself is like that is another part. Like it's not something we will handle now. If not, you guys just get lost. But don't worry about the subnetting right now. Like subnetting itself for now. That one will definitely treat that one. That one is something you rush. If not, if you don't get it, time is being taught. I don't know what to say. So we'll not rush into that. But I'll explain this again. So I said that an IP address is divided into two portions: the network portion and the host portion. And I brought in an analogy of a classroom. Okay. Saying, what if we have a classroom, science hall A, with 100 seats? Now we can call science hall A the network. The network portion of an IP address. Because if we have 100 people inside a classroom, they can all communicate with themselves because they are in science hall A. I don't know if you get so like science hall A itself can be called the network. Then the seat numbers can be called the host portion. Because if you come to science hall A today and you sit on seat number 1 because you came early, let's say the next day you come late, right? What happens? You might sit on seat number 50. You get now your host portion, that is your seat number, is changing. But what does not change? Science hall A is still in science hall A, right? So you're still in hall A, but what is changing is that okay, your seat is changing, but still you are in hall A. That is how the network portion and the host portion of an IP address is, right? So devices that are in the same network, sorry, excuse me, devices that are in the same network, they will always have like the beginning of the IP address will always be the same, right? So if say me, you, Rollins, and every other person on this call right now, we are in science hall A, we are going to have different seat numbers. So two people will not sit down on one seat, right? But we'll all be where? In science hall A. We'll all be in the same network. So that's how it is for network. That's how it is for IP address on devices. Devices that are in the same network will all have the same the same network portion. So if I have 192.168.1.200, 192.168.1.50, 192.168.1.5, they all have 192.168.1 in them. That tells you that okay, these guys are in the same network. The only thing that changes is the last number here. One has 50, one has 5, one has 10. So like I said, look at this as the seat number. Look at this as the what's it called? The hall, the classroom. Then the subnet mask. For now, just look at it like subnet mask tells you the network portion and the host portion of your IP address. For now, just look at it like that. So anywhere that has 0, your host portion. Anywhere that has 255 is the network portion. So if I have, hold on a sec. If I have, say, sorry, that's 1.100, right? Right? If I have these 3 IP addresses, and I tell you that their subnet mask is 255.255.255.0. From my simple explanation, which I said we should use for now, right? If I tell you that this is the subnet mask, it tells you that anywhere that has 255 will be the same. Anywhere that has 0 can be different. That is for you to know the devices in the same network. And if we look at these 3 IP addresses, the IP addresses are different at the host portion. But the first 3 octets of 255, 1, 2, 3, they are the same. So the subnet mask is what we use to tell you, okay, this is our network. okay, this is our, yeah, this is where our network portion is. This is where our host portion is. Subnetting now is deep, deep, deep. So if I do that now, you will definitely be confused, right? So let's not rush into subnetting, right? But for now, just stick with this. That your subnet mask lets you know the network portion and the host portion of your IP address. Do you still have anything to ask, or are you clear with that? All right, thank you. Any other person, please, before I move on to the next? Any other person? Okay, cool. So your, like I said, the IP address itself is 32 bits, which is 4 bytes, and each octet is 8 bits. So each of these numbers, convert them to binary. Each of them are 8 bits at the moment. And this is how the IP header is. The version that's either using IPv4, IPv6. This is the length of the header. This is what's it again? Diff service. Yeah, diff service. This is for QoS. This is the total length. This is the identification flags and all that. Then IP address is the operates at the network layer, right? And uh, this is like one of the addresses I said that a device must have to be able to communicate. A device without an IP address will not be able to send. Imagine your phone without an IP address, or when you try to connect via Zender without an IP. You know, you always turn on the hotspot to connect to the hotspot. At that point, you're trying to get an IP address. Now, moving on. Devices can have an IP address in two forms. It can be manually configured with an IP address, or it can automatically be configured with an IP address. It can request an IP address. Unlike the MAC address that's from the producers, right? For example, now my laptop is a HP laptop. Directly from HP, what's it called? They've already given it a MAC address directly from HP. Same as my phone, same as my smart TV, same as the watch, everything, right? From the producers, they give it an IP address. Sorry, a MAC address rather from the producers. They call it a they can call it either a bond address, that's BURNED, bond in address, or we can call it a physical address, right? So directly from the manufacturer, the device is given a MAC address. But now the IP address itself is the network address, and devices can either get that either manually, that is the network admin give their device an IP address, or they can get it automatically. And how do they do that? By the help of what we call a DHCP server. So DHCP stands for Dynamic Host Configuration Protocol. And what it does is it simplifies the process of assigning IP addresses to devices. All right. So if we have, I'm coming, please just give me. Okay, so as I was saying, DHCP stands for Dynamic Host Configuration Protocol, and it simplifies the process of assigning IP addresses to devices. So let's say we have you're a network engineer or a network admin, and they tell you to assign IP addresses to 1,000 devices. Imagine you manually entering an IP address for 1,000 devices. First of all, it's tiring. You're also prone to making mistakes, like, yeah, a whole lot. And there are like lots of other cons around. Well, DHCP now simplifies the process. What it does is you configure the DHCP server, telling it that, okay, this range of addresses, if a device should request an address, right, assign it to it. So I could configure a DHCP server, and I could tell the DHCP server that I could tell the DHCP server that, let me erase this, that 192.168.1.0 to 192.168.1. Let's say to use something with, okay, 1.127. I could configure a DHCP server telling you that within the range of 192.168.1.0 to 192.168.1.127, assign IP addresses to devices. So any device that requests for an IP address, give it an IP address within this range. So you can see how easy that is. You just have to do the configuration on one device, and the device can assign IP addresses. It's called leasing. It leases out the IP address to the device, and then they can, like, what's it called? It gives it like a lease time. For example, I have a router in my house. When I connect via DHCP, when I connect an IP address via DHCP, it's for 3 days. I can be connected to that router for 3 days straight, right? But on the third day, when the time elapses, what happens is that IP address will be returned back to the server, and I'll have to request for it again. So devices request for IP addresses via DHCP, and they do that by sending, I mean, devices successfully get an IP address by sending 4 types of messages, right? People give the messages an acronym called DORA, right? DORA. D stands for discover. O stands for offer. What else again? R stands for, I think, requests. Then A is for acknowledgement. Right? So whenever okay, for example, you could decide to turn on your Wi-Fi on your phone or your laptop and try to connect to your router, for example. You see your router keeps on, or your phone rather, would say something like obtaining IP address, that sort of thing. It is going through this process. It's doing this, right? The device, first of all, send this to the DHCP server, which is the router. The router will send the offer back, right? Then the device sends a request telling the router that it is accepting the address, and the router acknowledges. So this is the process of DHCP. This is how devices get an IP address. Any question on this, please? Any question on this? On the assigning of IP addresses? Are we clear on this? Should I move on to the next? Please, if you have questions, you ask for, please. I'm waiting for your reaction if I move on to the next. I'll just move like that. Am I still on this call? Wait, let me go check that on this call actually. All right, cool. So yeah, moving on. So DHCP, like I said, it simplifies the process of assigning IP addresses to devices, right? Easing you of the stress of manually configuring devices with IP address, okay? And all that. So with that now, so if our device has a MAC address and it has successfully been assigned an IP address, it can communicate on the network. That's just how it is, okay? And moving on now, what we'll talk about now, we'll talk about network devices, right? Network devices. And I'll start with the network switch. But before I start with the network switch, I don't know how many of us have laptops with Ethernet ports. Ports that are something like this, just one, right? So if we have our laptops with an Ethernet port, let's say we have 2 laptops, for example, and they both have Ethernet ports, we could decide to connect laptop A to laptop B via that port, and it will work correctly. We will connect them via that port. We could assign them IP addresses, and there we have a network, a peer-to-peer network. And that will work fine. But what if we have another laptop C, and laptop C wants to communicate with laptop A, but it sees that there are no ports for it to connect to on laptop A, because every laptop has one NIC port. Like for example, this ports we are seeing here, every laptop has one interface, right? Every laptop has one. Just like your, let's say your charging port, for example, every phone has one charging port. So let me use a charging port. I think that one is common amongst everyone. Okay. So let's say everyone has a phone, obviously, with a charging port. and we know that every phone has one charging port. If you connect the charger to that port, no other thing can go into that port unless you remove the charger, right? So if, for example, now we want to connect our laptops now, we want to connect our laptop to 4 other laptops, whereas we have just one interface that we can connect. What do we do? That's what the network switch, that's how it simplifies the connectivity process, right? Or let me use something more common. We have a wall socket and you want to charge your phone. You can decide to plug your phone directly to the wall socket and charge your phone. What if now you want to charge your laptop, you want to charge your power bank, you want to charge your AirPods, you want to charge a Bluetooth speaker, but you've already connected your phone to the wall socket. When you want to charge all those things, what will you do? You will bring an extension, right? Connect the extension to the wall socket and then connect your devices to the extension. And you can charge all of them simultaneously. That's how the network switch simplifies connection for devices on the network, right? So instead of having laptop A connect directly to laptop B, we could decide to connect laptop A to a switch, right? Connect laptop B also to a switch, and connect laptop C also to a switch. Now, with that, those three devices can communicate with each other in as much as they have one connection to the switch. Okay, so that's one of please take note. That's one of the importance of the switch. It has a high port density. You can see, for example, now this switch, for example, has this is 12, 24, has 48 ports. So meaning we can have 48 devices connected to this switch and they can communicate. Now, a switch itself operates at layer 2. Remember what I said layer 2 is, right? Layer 2 is our data link. And remember the address that I said works on the data link, the MAC address. Please take notes. The MAC address is what works on the data link. So a switch operates at layer 2, meaning it doesn't have any concern with your IP address. What it does is it forwards your information based on your MAC address. That's why I said it's very important for you to have your destination MAC address and your source MAC address. That's how the switch forwards data. Okay, now, it works at layer 2, though there are some switches that are also layer 3 switches that they work on layer 2 and layer 3. But let's just focus on layer 2 for now. So if I have a device, right, connected to port 1, oh, I think I have a picture on that. Yeah, good. So this is our switch. And now, for your switch to be able to forward data to another device, it must have that device's MAC address in its MAC address table. Right, so I'll explain. I said a switch works at layer 2, it forwards layer 2 addresses. And what it does is it has what is called a MAC address table. Right? It's a memory where it stores, or rather it maps a device's MAC address to the port that device is connected to. For example, let us look at PCA, for example. Now it has a MAC of 000A. That's what PCA has. And if we look at this MAC address table of the switch, you can see port 1, it's port 1 here, 000A. The switch does not know that it is the computer that is connected to 000A and it's connected to port 1, but it just knows that the device connected to port 1 has this MAC address. Please, let's really pay attention to this part. The switch maps your MAC address to the port that it's connected to in its MAC address table. That's why I said it works at layer 2. It works with MAC addresses, because if I have a let's go back to our frame, for example. If we have a frame with the destination MAC address of 000A, right? That is this device. What the switch will do is, okay, this one. What the switch will do is it will check its MAC address table to look for where 000A is and the port 000A is connected to, and then to send it out of that port. Do we understand, or should I go back? Should I go back or I should keep on going forward? Do you guys understand this? If you type in the chat, I think I would see it. So, like I said, switches have what's called a MAC address table, okay? And they map the device's MAC address to the ports the device is connected to. So that whenever it receives a frame destined for that device, what it does is it just forwards it out of that port. So that's some sort of like intelligence that a switch has, right? It doesn't operate like other, for example, in the prior to the technology of the switch, then they were making use of hubs. So, for example, a hub, if a device PCA wants to communicate to PCD and it sends that message to a hub, what the hub will do is it will send it to all the devices. It doesn't care even if this is not PCD, it will send it to all of them. Whoever device concerns will work with the device, they work with the data. So, but the switch now brings some sort of intelligence. So instead of doing that forwarding of all of them, it just checks its MAC address table and then sends that data out of that port. So for example, we have this frame destined for PCD here. Now, PCA has sent the frame. The switch has looked at the MAC address. This is where it concerns the switch here. This is where the switch looks at, just here. It doesn't look at any other place here. This is where it looks at. It says, okay, this MAC, this data, this message is destined for 000D. It then checks its MAC address table. Where is 000D connected to? It then says, okay, port 4. It will then forward out this frame out of port 4. Do we understand? Please, I need someone to reply. Please, I need someone to. Do you understand this? Hello, I hope you guys can hear me. Do you guys understand? Okay, cool. All right. So, like I said, the switch will look at the MAC addresses and then forward it out of the port. But in a situation where the switch does not have, let's say now this frame was destined for PCC, and from our MAC address table, we can see that PCC's MAC address table is not mapped to any port. What will the switch do? The switch now, in that scenario, the switch will forward that message out of all these ports because it does not have a MAC address to that device. Okay, so what we should know is this. All right, let me say this. How does a switch store the MAC address of device in its MAC address table? How does it know the address to store and the port to map it to? It does this by looking at, again, it looks at this, the source MAC address. So every data, every information you send, that every device sends, as long as it's from that device into this port, what the switch will do is it will just look at this portion, source MAC, and then add it to its MAC address table. So if PCB sends a message, it will then check its MAC address table. Do I have PCB's MAC address here? No, I do not. It then adds it port 2 PCB, puts the MAC address. Same as PCC. Do I have its MAC address? No. Port 3 MAC address. That's how the switch builds its MAC address table. It looks at the source MAC address of every frame, right? And then stores it. If it has the MAC address, it doesn't bother. So with this now, if the switch has built its MAC address table like this now, it now knows all the ports that each device is connected to. So if a frame comes in the switch destined for any of these devices, it doesn't forward it out of all the ports. It just forwards it to that device directly. That's how switches operate. Okay, that's how they operate. That's how they forward frames. And now, a frame can be either destined for a particular device, right? And this is, for example, here. If you look here, I wrote here unicast frame. That's what this is, a unicast frame. Unicast frame basically they're frames that are destined for a specific device. Now, let's still use iron runners now, for example. I'm trying to communicate with runners. I know that, okay, this message I want to send is directed to Rollins. What I do is I just say, hey, Rollins, and I tell him what I want to tell him. That is unicast. Unicast is a one-to-one communication, one device to another device communication. Now, they can also be broadcast frames. Broadcast frames are, before I continue, let's look at the destination MAC address of this frame that has been sent. 0007 E942 AC28. That is the MAC address of this server here. That is the unicast MAC address of the server. But what if it's a broadcast frame? How would you know that this frame is a broadcast frame? You know that by looking at the destination MAC. The destination MAC will have all Fs in this MAC address, something like this. If you look at the destination MAC address portion, right, all Fs. So whenever you see a frame with all Fs, you just know that, okay, this is a broadcast frame. What will happen is when the switch sees that broadcast frame, it will forward that message out of all the ports, except the one that it came in from, right? Forward that message out all the ports. So that's what broadcast frames are. And I know when I was talking about this, I said something about if the switch does not have the MAC address of the device, it forwards it out all the ports. That doesn't mean it's a broadcast frame. So let's say let's say for example now, right? For example now, this is not here for PC4, right? This is not. Hold on, right? So let's say for example now, PC4's MAC address is not on this MAC address table. What we have is just PC1's MAC address, and the switch receives the message for a MAC address 000D. It has seen in its MAC address table that I don't have this MAC address, so what do I do? The switch will flood that frame out. Now, that is not a broadcast frame. It still has a unicast MAC address. It still has a unicast MAC address, right? So it's destined for one device. But in as much as the switch floods it out, it doesn't make it a broadcast frame. A frame will only be a broadcast frame if it has a destination MAC of all Fs, right? So please, let's take note. If a frame has a destination MAC of all Fs, it's a broadcast frame. When it leaves that port, it's when it gets to the switch, rather, it's being forwarded out all ports except the incoming port, right? Another type of frame is known as multicast. Multicast is just a selected group of devices receive the message. Okay, group of devices will receive the message. That's just what multicast is. So let's say I'm looking for a simple way to do this now. Okay, yeah. Okay, let's work with WhatsApp, for example. If you block some certain contacts from viewing your status, right? The ones that are not blocked will be able to view the status. But the ones that are blocked from viewing the status, they won't view it. But they are still on your contact list. You can still text them, right? But when you post something on your status, the blocked guys, so let's say these are our blocked people now, they cannot view your status, but this can view. That's just what multicast is. Multicast is a selected group of devices, right? Selected group of devices will receive that frame. And also multicast have multicast frames, they have a multicast address. And they are being used for specific purposes, right? Specific purposes. So those are the three types of frames we have: unicast, one-to-one; broadcast, one-to-many; then multicast, one-to-few. Any questions? Any questions? Any questions? Okay, so I mentioned that a device will have to have it has to know the MAC address of the receiver. That's listen. Looking at this again, for example, PCA wants to send a message to PCD. It has to know the MAC address of PCD. What if it does not know the MAC address? What will it do? has to ask for the MAC address. PCD. That is what ARP is. ARP stands for Address Resolution Protocol. So what ARP is used for is it's used by device. It's a protocol used by devices to request for the MAC address of the device. So 192.168.1.5 wants to communicate with 192.168.1.8, but it does not have the MAC address of 192.168.1.8. What will it do? It has to ask for it. That's what ARP is. And ARP messages are broadcast frames. So I already drew a topology for this. So let me just show you work with that. Please confirm if you can see my packet tracer lab. Can we see this, please? Is this visible? All right, cool. Thanks. Right. So now I've configured each of these devices with an IP address, all right? Well, they've not communicated with each other before. So PC2 does not know the MAC address of PC3, neither does it know PC4 and PC3, and PC4 rather. So I said that for devices to communicate, they must have the MAC address. So now let's do this now. PC2 wants to send a message to PC4. If we look at the message it wants to send, let's look at the outbound parts. And okay, now if we look at the message that it wants to send, this is IP. This is our layer 3. If you look here, if you look at the values here, they are similar to what I showed you in my slide. The version, the length, internet header length, the DCP, DSCP, and all that, right? The IP address, that's the source IP, PC2's IP, then the destination IP, PC4's, right? And ICMP is also there. So this is our layer 3 information, but it does not have a layer 2 information. And for you to successfully send message, you must have layer 2 and layer 3 information. Why doesn't it have layer 2 information? Because it does not have the MAC, it does not know the MAC address of PC4. So what will this PC2 do? What it will do is it will now ask for the MAC address of PC4. It will ask PC4 for its MAC address. And I said that it's going to send an ARP, ARP, which is a broadcast frame. Now let's look at this ARP. Which this can be. I can't even zoom into this more. This should be okay. So now this is our app here. This is app, right? And you can see source MAC is that. This source MAC now is PC2's MAC address. Source IP is this. PC2's IP address. Now, if we look at the target MAC, you can see that it doesn't have, have the MAC address of the device is trying to reach. So, and the target IP here, it knows the IP address, but it does not know the MAC address. So what it means is the MAC address. That's why it's sending this app message. And if we look at the destination MAC, you can see they're all Fs. That's to tell you that it's a broadcast. So I'll tell you that it's a broadcast. So what will happen is when the frame gets to the switch looks at that and sees that, okay, this is all F, it's broadcast, and it will forward it out all the ports. So let me show you how that works. Now you can see that it got to the 3 devices. It's being discarded by these 2, but it's not discarded by this. This is because they've looked at the IP address, right? And they've seen that, okay, that's not the IP address. That is the IP address here. Target IP. It checks their own IP address and says, oh, that's not mine. That's not mine. But when this guy looks at it, he says, oh, that's mine. And what it will do is it's going to send a message now. The source MAC, which is its own MAC address, it will send that back to PC2, telling it that this is the MAC address of device connected with this IP address. Right? That's just what it's going to do. And now the message that we want to send before, remember it had only IP, it had only layer 3 information. Now it has layer 3 and layer 2 information. And if we look here, you can see added this MAC address and the MAC address of the receiver. So that's how devices can successfully communicate, right? They must have each other, they must know who they are sending the message to, what's and the destination, both the layer 3 and the layer 2 destination. Any questions, please? Any questions? Any questions on how? Okay. The next. So now, what is a router? What the hardware switches? So a router is a network device that operates at layer 3. Remember I said that the switches they operate at layer 2. Routers are they operate at layer 3. And they do this by they do this by looking at what concerns them being IP addresses. So they work with IP addresses, they forward data based on IP addresses, right? So if we should send I don't know if I have right. So if we should a device here, I also have a topology for that I'll show you. This device wants to communicate with this device. What it to do is it knows that okay, it has seen that they are in the same network. If you look at the IP address, right, 192.8.10.10, that is its own, and is destined for 10.1.2.10. It has seen that we are not on the same network. Just like looking at our classrooms again, for example, Science Hall A is different from Science Hall F. I want to send a message to somebody, and I've seen that this person is in Science Hall F. That kind of a thing, right? We are not on the same network. So when devices have done the calculation and they've seen that I'm not on the same network as who I want to send a message to, what do? They forward a message to the router. So that's the job of the router. The router gives connectivity to devices at layer 3, right? So if a device wants to send a message to this device, it knows that I have to send this message to my router. It will send a message to the router. The router now, what the router does is it has what we call routing table, right? A routing table is where it stores path, like it has a path to get to certain routes, right? It stores that in this routing table. So when it receives a packet destined for a network, it checks its table, and if it has a route to that network, it forwards it to its next hop. So the next hop being like the reason you can hear what I'm saying, the reason you can receive a message on WhatsApp, the reason you can access YouTube or anything is because there are routers in between that have a path to that network or that service you're trying to request from, right? They have a path to reach there. So your device, when you send a message, if you're connected to the router, when you send a message to someone on WhatsApp, the first place the message gets to is your own home router. That's the router you're connected to. From that home router, it goes to series of routers before it gets to the destination. So that is how it is, right? That's how it is here. If you send a message, if you see that this person I'm trying to reach is not on my network, what happens is the message has to go to the router, after the router to the next, and like that. But if you have devices now, let's assume I'm connected to a router, and you want to, let's say, CZ Rollins again. Let's say I'm connected to the router, and Rollins is also connected to the router, and I want to send him a message on WhatsApp. We are both connected to the same router, so we have the same network. So as I send the message, what happens? The message now will go to my router and then to Rollins. When I send him a message, it goes to my router. It doesn't get to the router this time, rather. It goes to the switch. I'm looking at it physically now. it goes to the switch and then to Rollins. So looking at, let's work with that our topology again. Let's say here, for example. Let me add another device here. Sorry, add another device and just give me a minute. Let's give an IP address. So 192.168.1.5. Sorry. So now let's say this is me and this is Rollins. I'm trying to communicate with Rollins, right? And I send a message to Rollins. This is the first one we just talked about app, right? It's asking for the MAC address. Rollins sends back his MAC address to me, and then I send him the message, and then he sends a reply back to me. This is how communication works. But what if I'm trying to reach this guy? Obviously, let's say this guy is somewhere in Abuja. Okay, let's say this guy is somewhere in Abuja. And he's let's say we are somewhere in Lagos. Right? I'm trying to communicate with this guy. I've seen that I'm not connected. I can't reach this guy. We're on different networks. So my network is 192.168.1. Network is 192.168.2. What do? I will send it to my router. Devices always believe that the router always has a way to reach where they are going to. So they send it to the router. So the job of the router now is to check each routing table and know where to forward message to reach that destination. Okay, that's the job of the router. So the router now is known as the default gateway. That's what it is. It's known as default gateway for this network. It's known as default gateway, meaning that if you cannot reach this person, if you checked and seen that you can't reach this person on your own network, send this to your default gateway, send it to me. Like the router is kind of like the door to that hall, science hall A, for example. We are trying to reach somebody, we've seen that this person is in science hall F. What do? I have to leave science hall A, which is the door, and go to science hall F, the door of science hall F, and then reach who I want to reach. That's what the router is. So the router will receive that message and forward it down to whoever you want to send the message to. Like, oh, sorry, I'm supposed to show you this in real life, in real time. Yeah. Simulation. So I'm trying to reach someone in science hall F. I send the message to my router. The router sends it to this one because it knows that, okay, if I want to reach here, I should send it to this router. And this router does back and, same thing, sends a reply and it's successful. Right. That's how routers, that's how they forward frames. They use MAC addresses. But one thing we should know is, okay, this is an example of a routing table. Let me just show you the routing table of the router we just worked with instead. Yeah. Show you here. So this is the routing table of our own this router we just worked with. This S stands for static route. I won't go into different types of route for now, but just know that this is the reason why we can reach that network because of this guy here, this static route that has been configured. We are telling it if you want to reach 192.168.2.0, right? Send it to 172.168.1.2, which is the IP address at this interface. This is 172.168.1.1, 172.168.1.2. I won't really go down deep into that, right? So we don't get too confused. But yeah, this is another example of what a router's routing table looks like too. This, right? So now let's look at this now. This person here in PC1 is trying to access the web server, okay? And it has seen that the web server is not in its network. So it has to send it to its router, the router down to the next one. Like it has to send to its router, and the router should find a way to reach because it believes the router knows. what happens is, remember, I said something about, I don't think I did, sure, but MAC addresses, uh, they don't, every device's interface has a MAC address. And MAC addresses are not, what do I put it now? For example, I want to send a message to the web server right now. My MAC address is AAAAA. The destination MAC will not be, it will not be this device's MAC address. It will be the MAC address of my port gateway, because MAC addresses are layer 2. They are not forwarded. They're not forwarded like MAC addresses wait on layer 2. So if I'm sending a message to this guy, that's how devices now, that's how they send a message to their default gateway. They don't send it with an IP address of, let me show you what I mean. Let me show you what I mean. It's going to be easier like that. So let's work with this again. Let's look at this message, for example, now. You're trying to reach someone in another network. If you look at the destination MAC address 000E00E0F91BE801, this MAC address now is this MAC address, right? Is not the MAC address of the device you're trying to reach. It is the MAC address of this router's interface here. Because MAC addresses are not forwarded from one network to the other. Right? They're not forwarded from one network to the other. So when it gets here, what the router will do is when it receives, that's how the router knows that this is for me. Let's look at the IP address. The IP address is 192.168.2.2, which is the device's IP address here. The source IP address is this device's IP. How does the router knows that, okay, this person is trying to reach the other network? It's from here. It looks at the layer 2 MAC address. It sees that, okay, this is destined for me. So it's here that the router now looks at and says, okay, this is for me. And then it strips off this Ethernet header and then looks at the IP where it's trying to reach. So for every hop, right? Let's assume there were 10 routers before this router. The MAC address will be, the source and the destination MAC address will be changing. When this message gets to the router will then change it. The source MAC address will be its own MAC address here. The destination will be this site's MAC address, just like that, until the message gets to the end. That's what is happening here, right? That's what is happening here. AAA is this device's MAC address down to router 1, right? That's 11111 like that. When router 1 wants to send the message, it will send it to this other router with a different MAC address, a different source MAC and a different destination MAC. When this router wants to send it to router 2, the same thing, a different source MAC, a different destination MAC. Until router 2 wants to send it to the web server, that's how it works. So when your information, when data is traversing a network, the MAC address, the destination and the source MAC will keep on changing. The destination and source MAC will keep on changing, but the IP address will always remain the same. Okay, so that's one thing you should also know. That's how devices communicate in the network. As I'm communicating with you, you can hear what I'm saying, because the IP address is, it's getting to, I think we're making use of Cisco WebEx, right? It's getting there and then it's being broadcasted us here. But the MAC address that from the originator, that's my laptop's MAC address, will be it will be the same down to the end. It will keep on changing as the packet moves from one router, the other router, to the other router. So that's how devices they communicate, right? The IP addresses will remain the same. The MAC addresses will be different in the network. So yeah. And okay, this is the last okay. Before I would see that's everything, I think there are some other things we should talk about. Okay. So for example, how do okay, let me talk about the transport layer before we close the session. Right? That's the transport layer, layer 4, the OSI model. So there are two protocols that operate there, TCP and UDP. And there are scenarios where you make use of which, right? First, TCP. TCP is used for devices that cannot, for data or messages that cannot handle loss. For example, imagine you are trying to send a mail to someone and you send the mail, but the person could not get everything. It makes no sense, right? So what TCP will do is it will make sure that that mail you're sending, the person gets every bit of that mail. So that is, it makes sure that it's the mail is delivered to who it's meant for. So it provides that reliability that whatever you are sending will definitely get to the person you want to send it to. If there is a mistake in it, if there's a mistake along the way, it will tell you that you should send the message again. All these things happen so fast, so you won't even know that it's correct. That's why if you're like working with slow networks, for example, and you're trying to access a web page, sometimes you can see that the web page will be downloading the some sections one by as in bit by bit, maybe text, picture, like bit by bit. That is what TCP is doing. It is making sure that you get every bit of that, no matter the speed. Maybe where there is like a packet loss or something, it will request for that particular section again, that segment, to request for it again, even without you doing anything. But now UDP now it works with messages or data that operates in real time, right? Like, because TCP, if there is a packet loss, TCP will stop whatever is going on. Like, it will request for that packet again that has been lost. But imagine you're hearing me speak, and let's say something happened to your network or to my network, and what I'm saying, you couldn't hear some certain part of it. What happened? There's no way that you can get that part back. That's because in real time, video conference, voice, you're working with UDP. UDP now, it doesn't care about reliability. So anything that you lost has gone. Just continue like that. All right. And so the protocol or the data or the service you're trying to reach, right? The service you're trying to work with. Each of them make use of certain transport protocols. And these transport protocols, I want to make sure that these devices communicate and they can like communicate with each other. Because another thing about TCP is connection oriented, meaning before you can send anything or before you can receive anything, there must be a connection. Before PC1 here can access the web server, they must connect first. There must be that TCP synchronization within both of them before they can start sending and receiving data. But for UDP doesn't even care, right? It just keeps sending, like that. So imagine, for example, a YouTube stream or Instagram live stream and all that. If there's a packet loss, the person will continue doing what he or she is doing. But nothing will go back. You will still, wherever your internet picks up from, you continue from there. That's what that's a brief explanation of the transport layer. And the transport layer now, what is being used there are port numbers, right? These port numbers are they are categorized actually. There is the well-known port, there is well-known port numbers, the registered port numbers, and ephemeral, I think what it's called. So the well-known are those ones are already, they have protocols assigned to them. That's for well-known. I think they start from, what is it, from 0 to 1023. Those are well-known ports. So, and most of the protocols we make use of, right? Your mail, your email, your what else? SSH, your telnet, HTTP, HTTPS, all of them, for DNS, DHCP, they fall within that range, the range of the well-known. Then for your if you're trying to, I don't know how many of you are trying to like work with create like web servers on your system, right? You can see most of the times you get port numbers like 8,000, 8080. That range from 1024 to I think 49151. So that range is known as the register. So most servers you're trying to work on, most of them come from there. But your device itself, when it's trying to access, like I said, what numbers are being utilized. When it's trying to access web services, your device will get port numbers from the ephemeral. Okay, that's how it's been figured. So devices will make use of port numbers to communicate. So even those port numbers also are being used. That's why you can have multiple tabs open on your browser and different information there, because it's been like port numbers are being made use of. So each of those tabs, right? Each of those tabs will have like different port numbers that have been, like, so this is just like a brief, a very, I don't even think this is even brief. This is a very brief intro to what networking is all about. There is a lot, like there is a whole lot. Even me, sometimes when I'm even studying currently, like it's crazy. I won't lie. There is a whole lot to expect, and yeah, it's not hard per se. Just if you're ready to read, networking is actually straightforward, and yeah, I'm sure you guys will be enrolled in the course, and it's the course itself is actually quite simple. These things I've talked about, they talk about it well, like, and they even give more explanations and all. And there are also labs and quizzes you can work on. So with this, I think this is where I would stop. Where I'll stop for the brief intro to networking. And I do hope to hear from you guys some other time.